mosquito. 90 million years of evolution have turned it into a perfect life form. Equipped with a sense of smell many thousands of times better than the human version, mosquitoes can smell their prey kilometers away. Their antennae are covered with thousands of tiny hairs capable of receiving and analyzing information about odors in their surroundings. Mosquitoes can identify many different odors, and this enables them to home in on mating partners and, more particularly, the blood of humans and animals. The mosquito draws blood through a bite in the victim's skin. During this process, malaria pathogens can be transmitted. There is no known substance that can effectively stop a mosquito from biting once it has located its victim by its scent.
Mosquitoes do have remarkably keen ability to detect odors in the environment. There are a number of diseases whose host is first the mosquito, and then upon biting, takes up residence and causes disease in man.
Every year, 1 million people worldwide die of malaria. Every 30 seconds, a child dies in Africa to the tropical disease. Malaria is continuing to spread because mosquitoes have developed resistance to all the products conventionally used to control them. Professor Richard Axel from the United States discovered how the sense of smell works in humans and insects and won the Nobel Prize for this work in 2004. His fundamental research demonstrated that odors, such as those contained in human sweat, dock onto specific receptors in the olfactory cells, activating them and transmitting an electrical impulse. On the basis of these findings, Richard Axel is now working with researchers at Bayer to develop a groundbreaking approach.
And indeed, Bayer, through a remarkable laboratory, identified a large number of structural classes of chemicals that do block these receptors.
The sense of smell works like this. The hairs in the mosquito's antennae contain pores through which odors are transported into the scenting hairs. The odors dock onto a binding molecule which transports them to special receptors on the nerve cell. One part of the receptor binds the odor, another controls the channel. This channel is identical in all receptors. Upon binding of the odor, the channel opens and allows electrically charged ions into the cell. Electrical impulses are sent to the mosquito's brain. This is how it smells. Like an odor, the potential Bayer compound should also enter the scenting hairs. It would be transported to the receptors by the same binding molecule that transports the odors. When it docked onto the channel part of the receptor, it would prevent the channel from opening. Without the corresponding electrical impulses in its olfactory system, the mosquito would be incapable of finding either food or a mate. The new approach interferes in the mosquito's olfactory processes at a more specific level than previous attempts. It is now possible to interrupt the entire olfactory chain with a single active substance.
So our goal is rather simple. It's to understand the nature of the receptors on the nose, the antenna of the mosquito, that respond to odors emitted by humans. And if we can block that interaction in a meaningful way, we feel that we can have a significant impact on reducing biting.
The first compounds to emerge from screening Bayer's substance library are now being tested. Fluorescence testing shows whether they are effective. If the cell doesn't light up, it means that the compound is effective because no electricity is flowing. The sense of smell, which the mosquito needs to survive and reproduce, has been knocked out. This new approach to beating malaria is just the first step. We are looking at developing a completely new generation of active compounds, which can also be used against parasites and insect pests. Even though years of intensive research will still be required in this field, Bayer's approach offers some promising perspectives in the fight to control malaria.